Now, there's actually a stronger result, and it goes as follows. Let's take our matrix A, and let's view it as its diagonal, which is where these points in the complex plane where the disks are centered are, plus its off-diagonal part. And then let's parameterize this by introducing a parameter omega. So now we have a family of parameterized with omega that ranges from when omega is equal to 0, it is purely the diagonal part of A, and when omega is equal to 1, you end up with the matrix A. Okay? Now if you think about it, when omega is equal to 0, this is just the diagonal matrix, and what we know is that its eigenvalues are just the values on its diagonal. And you can think of the Gershgorin disk theorem saying an eigenvalue lies in the disk of radius 0. Well, all of the eigenvalues lie in the union of the disks of radius 0 around those points. But we actually know that those points are the eigenvalues of our matrix D, of our matrix A of 0. Okay? Then we can start varying our omega. And an insight is that where the eigenvalues of matrix A are varies continuously with this parameter omega. And that's another argument. But as far as the Gershgorin disk theorem is concerned, what this means is that when omega is very small, these disks are very small. And because of this continuity argument, what we know is that only eigenvalues that were in the disk when the disk was smaller are now still in the disk as long as these disks stay disjoint from each other. And it's only when these disks start overlapping that an eigenvalue from one disk could wander into the other disk. Well, what this means is that when finally omega is equal to 1, you're back to the conditions of the Gershgorin disk theorem, but what you now have observed is that the number of eigenvalues that are in the union of a set of overlapping disks is exactly equal to the number of those overlapping disks when those overlapping disks are disjoint from all of the other disks. Okay? And that allows you to better qualify and quantify where the eigenvalues might be.